Hello everyone, and welcome to this presentation on modeling and control of a wave energy converter for maximum power extraction. The main purpose here is to show that the amount of energy extracted from motion waves using wave energy devices can be increased by using appropriate control strategies. First of all, we will have a brief introduction on wave energy. We will see what is the status of wave energy in the world today. We will also look at different wave energy devices, in particular the point absorber type, which is the device we actually used in this work. Then we'll move on with the control part as applied to wave energy converters. We will see how can control methods be used in the field of wave energy. The next section will be about modeling, where a complete model of a wave energy converter was created using Simulink and MATLAB. We'll look at some results obtained during the simulation. We also attempted to design and build a small-scale prototype of a wave energy converter and a wave tank to try and confirm the results that were obtained during simulation. We will see the different problems that we had during the implementation and why the prototype did not behave as expected. Finally, we'll draw some conclusions based on what we have seen during this presentation. Let's start with the introduction. So, wave energy can be simply defined as the useful energy that can be captured from ocean waves. These are produced by winds blowing over the surface of the ocean due to temperature differences caused by the sun. According to the World Energy Council, the global resource of wave power is approximately 2 terawatts. Alberton Wave Energy Limited actually produced this figure showing how this resource is distributed across the globe. Regions in red receive more than 60 kilowatts of power per meter, orange regions 40 to 60, yellow 30 to 40, and so on. According to different estimations, 5 to 25% of this resource can be extracted using wave energy devices. This, together with the fact that wave energy converters can operate 90% of the time, make wave energy a viable source of clean energy. The chart shows the global energy consumption by source. As we can observe, only 19% of the energy that the world uses come from renewable sources, and from those 19%, wave energy represents only 0.001%. So the question is, why so low amount? This is mainly because of the high initial costs of building a wave energy conversion system and the numerous failures that occurred in the past while attempting to build efficient conversion systems. Currently, there are only 4 commercial wave power stations in operation in the world. There exist many types of wave energy converters that can be classified as onshore, offshore, or nearshore depending on where they are placed. The first type is the attenuator type wave energy converter. Attenuators are generally placed in parallel to the force and the wave direction and capture energy from motion of each arm relative to each other. Then we have the oscillating wave surge converter. For these devices, the arm and the flap is mounted on a hinge fixed to the seabed. The arm moves to and fro with respect to the movement of the water. On the right we have the aquamarine oyster. When the flap moves, it drives 2 hydraulic pistons which push hydraulic fluid through a flow line connected to a turbine and a generator found on shore. This means that energy is extracted near the shore, but electricity is produced onshore. As I have stated earlier, there exist many types of these devices and we will not cover all of them in detail. I'll just quickly show you 2 more before going to the device that we actually used in this work. So this one is the oscillating water column. Here energy is produced by air pressure changes due to rise and fall of the water column. Next we have the overtopping device. When a wave is incident onto a device, water is captured in the storage reservoir, and this water is then funneled through the hydro turbines into the sea. The device that we are actually interested in is this one, the point absorber type. It consists of a floater or buoy which moves up and down with the wave and drives a system called the PTO, the power takeoff system. The buoy is connected to the PTO via a wire or shaft. The PTO simply converts the up and down motion into useful energy to drive a generator. PTOs can be direct drive or hydraulic, depending on the situation. The main purpose of the control system is to increase the amount of energy that can be extracted by the wave energy converter. And we must be able to implement the control method without modifying the structure of the wave energy converter too much, because here we are not trying to improve the design of the wave energy converter itself, we are only trying to control the existing system to get more power. So how can we get more power? For point absorbers, the condition for maximum power extraction is that the velocity of the buoy must be in phase with the excitation force. Excitation force here is the wave excitation force, which is the force exerted on the buoy by the incident wave. We can put it in another way and say that for maximum power extraction, optimum oscillation must be achieved, and this is achieved only when the buoy is in resonance with the incident wave. Let us take a look at this formula representing the natural frequency of the buoy, omega n b. So for resonance, omega n b should be equal to the frequency of the incident wave, but the ocean waves have varying frequencies, so omega n b must also be variable. From the formula, only A, the plane area of the buoy, and mb, the mass of the buoy, can be varied. The implementation of a method to perform these changes is, however, unrealistic. An alternative approach is to force the motion of the buoy to be in phase with the wave without changing its natural frequency. In fact, this is what most control strategies do, but the majority of them can only be used for analysis and cannot be implemented in real life. Currently, the simplest and most efficient control strategy that can be implemented is latching control. Latching control, it consists of locking, that is latching the buoy at certain moments and then releasing it after a certain time interval. Locking is done when the velocity of the buoy is 0. So let us consider a buoy moving in a moving wave. Now, at the extreme points, velocity of the buoy becomes 0 and the buoy is locked. After a time interval called the latching time, the buoy is unlocked. Meanwhile, the wave continues to move. As you can see from the figure, at some point the buoy may be partially or completely submerged, and so when it is unlocked, it will immediately accelerate upwards. Then the whole process repeats again, that is, it is locked again at another extreme point, and so on. Latching time is given by the following formula, where T latch is equal to TW minus T naught over 2. TW being the wave period and T naught being the natural period of the buoy. However, this formula is applicable only for regular waves, and ocean waves are mostly irregular. For irregular waves, latching control becomes non-causal, and so we must find a way for wave prediction. Wave prediction is tedious and will not be covered in this presentation. Instead, we make use of a suboptimal method, in this case suboptimal latching. For suboptimal latching, we have the same condition as for locking as for optimal latching. For latching, we make use of different schemes. We look at two of them. The first one, latching is done when the excitation force changes direction with reference to the surface of the ocean. If you recall the condition for maximum power extraction, that is, velocity must be in phase with excitation force. In simple words, Scheme 1 only tells us to unlock the buoy when the velocity and the excitation force are in the same direction. Scheme 2 tells us that the buoy is unlatched when the wave surface elevation exceeds a certain threshold. And this threshold is given by this formula. If we compare the two schemes, Scheme 1 is more efficient but extremely difficult to implement. We can use Scheme 1 for simulations and Scheme 2 for implementations. Okay, let us move to the modeling part of the presentation. First of all, we'll look at the modeling of the motion of the buoy. The motion of a body in three-dimensional space is characterized by 6 degrees of freedom, 3 translations and 3 rotations, as seen in the figure. In this work, we consider the buoy having only 1 degree of freedom, namely heave. This is sufficient in this case, since the PTO mechanism that was implemented produces energy only from heave motion. Hence, the other degrees of freedom are irrelevant here and can be ignored. Oscillating buoy will be affected by multiple forces acting upon it, among which hydrostatic force and hydrodynamic force. By applying Newton's second law, an expression describing the motion of a heaving buoy with respect to these forces can be found as follows. In this equation, m is the equivalent mass of the whole system, including the inertia of the PTO. X double dot is the acceleration of the BOI. Fp is the wave excitation force, which is the force exerted by an incident wave on the BOI. Fs is the hydrostatic force, the force acting on the BOI due to displaced water when it is at rest. Fr is the radiation force. The oscillation of the BOI in water will create waves, and the force exerted by these waves on the BOI is called the radiation force. Finally, we have FPTO, which is the PTO force or load force. It is simply the force exerted on the system by the power takeoff mechanism. Viscous and moving forces were, however, neglected during the establishment of this equation. These different forces can be described by the following equations. As it can be seen, the time domain expression for both radiation and excitation forces contain a convolution term. Due to this, the two expressions can be approximated to state space models. Hydrostatic force is given by minus ksx, where ks is the hydrostatic stiffness and x is the displacement of the BOI from equilibrium position. For ease of modeling, the PTO was considered to be linearly damped and was represented by this equation. Here, FPTO is equal to minus BPTO x dot minus KPTO x, where BPTO is the PTO damping coefficient and KPTO is a constant. However, this is not a realistic representation of actual PTO systems. Our equation of motion was then implemented on Simulink. As it can be seen, a state space block was used to represent the radiation force here. State space parameters A, B, C, D, and the hydrostatic stiffness value can be obtained through complex algorithms like WAMIT or its free counterpart NEMO. We just feed certain inputs in the program, for example, shape of the BOI, its dimensions, its coordinates, direction of incoming wave, the depth of water, frequency range of waves, etc., and the program outputs our modeling parameters. The PTO was simply modeled using two gain blocks, according to the equation that we have seen earlier. The latching control modeling was the most difficult part in the wave energy converter modeling. The modeling program was divided into two parts. The first part is how, and the second part is the when. How will the locking of a BOI be represented in the model, and when will latching and unlatching take place? The approach for the first part was to cancel out all the forces acting on the BOI, that is the excitation force, the radiation force, and the hydrostatic force, by applying another force known as the latching force. This force also includes a proportional controller that will prevent the BOI from returning to its equilibrium position by blocking it at its current position. A PD controller or a PID controller could also be used. Latching the BOI is fairly easy since we know exactly when the BOI should be locked, that is when the velocity is equal to 0. This condition can be detected by passing the velocity through a heat crossing graph, which will output a Boolean true signal when the velocity reaches 0. The real problem is the latching part. To model this, the suboptimal latching scheme 1 was considered. This model constantly compares directions of excitation force and velocity. If they have the same direction, this means that the purpose of latching has been reached. The BOI and the wave are in phase, and the BOI will be unlocked. It can be assumed that latching is the default state of this system. The complete model is as follows. It consists of the different submodels that we have seen earlier. The BOI model here, the latching model here, and the PTO model. Here are the results of the simulation. The first set of results are for no latching control applied. So these are for regular waves, the top graph showing the BOI position and the bottom showing the BOI velocity. We can see here that the BOI displacement in red follows exactly the wave elevation. Same observations can be made for irregular waves. Now with control applied, you can see that the shape of the BOI displacement graph has changed. We can clearly see when the BOI is unlocked and locked. Here, for example, the BOI is locked at an extreme point, and then it is unlocked after a certain time interval. Also, peak velocity value, as we can see from the graph, is much higher now. Again, similar results for irregular waves. Locking and unlocking at different moments can be seen right there. If we now compare velocities, here for regular wave, we can notice a clear increase in peak velocity, an increase which is also noticeable with irregular waves. Comparing instantaneous power for irregular waves, we can observe a net increase when control is applied. Red is without latching and blue is with latching. We obtain an increase of approximately 500%, which is more than theoretical values. Theory suggests a range of 100 to 300%. Here, this discrepancy can be accounted for by the simplistic modeling of a PTO. However, this does not change the point that we wanted to prove here. Applying latching control does increase the amount of energy captured by a significant amount. Okay, we'll now move on to the implementation part. First of all, a testing environment was required. This took the form of a wave tank. The wave tank helped us to study the interaction of the buoy with the waves and of course to test the system. The tank itself is made of glass and has dimensions of 1 meter by 45 centimeters by 40 centimeters. The wave generation mechanism was designed as follows, with the different parts are shown. The paddle, the component in white here, is hollow and impervious and is made from composite aluminum sheets bonded together with a silicone adhesive. The paddle pushes the water forward by moving up and down, thereby generating waves. This up and down motion is called reciprocating motion. The height of generated waves depends on the range of vertical displacement of the paddle, and the frequency depends on the rate at which the paddle moves. Also, the front of the paddle is slightly curved, so that to facilitate the displacement of water. Here we can see a picture showing the wave tank in operation. You'll notice that a glass panel was placed at an angle inside the tank. This panel here is called the beach. It absorbs energy gradually from the wave so that a traveling wave may be obtained. Without the beach, a standing wave will be obtained when the wave is incident on the right panel of the tank. The following system was designed for the PTO. Let us break it apart to better understand the operation. The two main components of the system are the mechanical arm on the left and the ratcheting mechanism on the right. The mechanical arm simply converts linear vertical motion into a rotational motion. The ratchet mechanism allows rotation in one direction only. In the configuration shown, the gear can only rotate anti-clockwise, while clockwise motion is blocked by the pole here. The system consists of two mechanical arms and two ratcheting mechanisms. When the buoy moves up, only the right-hand side of the system is engaged, driving the flywheel anti-clockwise. When the buoy moves down, only the left-hand side of the system is engaged, again driving the flywheel anti-clockwise. What this system does is simply convert bidirectional linear motion of the buoy into unidirectional rotational motion of the flywheel. The role of the flywheel here is to store energy. Even when the buoy is docked, the flywheel can still rotate and drive the generator. The build is as follows. The structure is made of wood, with the mechanical arms made of metal and the flywheel also made of metal. The problem with this system is that it requires a large force to move, a force which cannot be supplied by a buoy of small dimensions. And we cannot increase the dimension of the buoy because of the dimension of the wave tank. Using larger buoys in the wave tank would distort the generated wave. So instead, the solution that we investigated was to use a PTO of smaller size. The following PTO was used. It is a simple direct drive PTO consisting of a rack and pinion system connected to a generator. Even though it requires a much smaller force, the buoy had still some problems to properly drive the PTO. So for future works, the solution would be to use a much larger wave tank instead of trying to miniaturize the wave energy converter. So what conclusions can we draw from this presentation? First, through simulations, we have proved that energy extraction can be increased with latching control. Also, we found out that suboptimal latching can give near optimum results. So this technique could be used instead of more complex optimal methods. Among the existing control strategies, very few can be actually implemented, and so there is a need to develop more practical strategies instead of purely analytical ones. We have arrived at the end of this presentation. So before finishing, let me just show you a small demonstration of the prototype that was built. Thank you very much for your attention.